when the red shows up, good. Okay. So after the snow break, we come back for the lipids, chemistry, and application 3. We will be very briefly go over the first two things, then we're going to spend a lot of time talking about the auto-oxidation. Okay, we're going to talk about the two lipids reaction. The first of all is esterification. Okay, this is very easy to understanding. You have R1 COOR2, which is glycerols, and you combine with R3 COOR4. Okay, what are you going to do? They usually need a catalyst. Sometimes it's a metal, and then will be recombined of those glycerol bonds. So esterification, the esterification will be recombination. So it becomes, for example, COOR3 and R2 COOR4. So which means there is a new products has been generated. Now, there is something we want to mention. This is usually happens for commercially manufacturing margarine. For commercially manufacturing margarine and the shortenings. This is kind of thing we're going to mention again for these two products. Now people will say, because hydrogenation we're going to mention again, people will say they may not be very healthy to eat, but they are very stable, which is from the shelf life point, it's very stable. And we think it's not safe because we may eat too much sometimes. But you need to know that's because we somehow is a little bit rich. People in African countries, in poor places, those are kind of a good energy resource. So there is a bad thing and the good thing for those products. And also the snacks, let's say a bag of the chips. Some people will say don't eat that too much because lots of stearic gases and also palmitic acids, yeah, they're not good for health. But you know, if some people in poor area, in poverty, if they have a bag of snacks, chips, and maybe save their life. So there's a good thing for them. Okay, margarine and the shortenings. The second thing is that this is usually happened, although we do esterification, but the level of polyunsaturation will not change. So which means when we do these esterification, if you have a very long chain polyunsaturated fatty acids, does not mean it will be changed, which means they're not going to add any of the hydrogen atoms in. And this could be happen below or above melting points. Now, what's the reason they do this? Because when you have an enter-esterification, at the end of the day, there is a new products generated. So, the character quality of fatty acids will be changed. Typically, is crystallization and melting points will be changed. Which means the characteristics of fatty acids will be changed. So that's why people want to do that. Okay? And this is, if you want to say very strictly, this is redistribution and needed catalysts. And the fatty acids radical move between hydroxy position. Okay, so I think we covered all of these. Now just give you a very easy example. This is a mixture equal amount of two simple glycerols, which is toluene and trostarium. When they combine together, we have an acronym SSSOOO. How many different combinations we have? We have 6 different combinations, and the frequency is between 12.5 to 25%. Now we also have a formula for that. This slide shows you the formula. If we have theoretically triglycerols composed by N fatty acids with molar fraction A, B, C, D, then what is going to be the total theoretical calculated combination? If we say N equals 4, based on this, you will see divided by 2, and that is N equals 3. If you do a calculation, that's 64, 6, 16, 8, 4, 3. This almost equals 20. Okay, so if there's a 4 fatty acids, 4 fractions, there is a 20 possible combination after esterification. Now, this gives you an example of cocoa butter. And this, we said very simple. They use its solid fat index to measure the fatty acids amounts in coconut butter. After interesterification, what tells us? A chocolate is no longer a chocolate. When you look at here, this is the solid fat amount in there. Okay? That is equally about 80. At room temperature, it's going to be dramatically dropped. When you put it in the mouth, if it's 35 degrees Celsius, it drops to 0 because it's melted. Okay? That is a good thing for chocolate. But how about if we do the interesterification? I think it's a stereo specific number place 2 if it's changed. This very steep curve will become a little bit flat. So what happened? Put in the mouth, the fatty acid is still there, the fat is still there, until you heat it. So you can say the chocolate is no longer chocolate, it becomes a lard. Because if you go back to see the curve, this curve is for pork lipids, pig lipids, which is lard. Okay? So that tells you interesterification completely changes the fat index will be impact the melting points, then the characteristics, the quality of the products will be completely destroyed and changed. So chocolate will become a lard. Okay, so let's give you an example. Now, I'm not going to go detail about the mechanism of the esterification. Our textbook has it. That's basically all chemistry, so I just skip that one. But you know what happened for the esterification. Okay, second one is hydrogenation. This is the one we mentioned briefly before. We will be mentioning maybe a little bit detail right here. Now, hydrogenation is same thing to making plastic fatty acids products, margarine and shortening. Hydrogenation. And which is how they do the reaction. It's a closed vessel. You, of course, you're going to put oil there. Then you're going to put the powder of hydrogen. Okay, then we need some of the catalyst, which is usually the nickel. Then we put a pressure and we put certain high temperature. Let it be agitated. Then we'll have hydrogenation happens. So the basic reaction looks like that. Is hydrogen adding to the double bond. So it's very simple. Okay, we're going to add here, becomes this. That's a hydrogenation. We need a closed vessel with oil. Of course, it's mono or poly unsaturated fatty acids. We put temperature, certain temperature, high temperature. Give a pressure during the agitation, then this is going to happen. Now, of course, we know the results because the double bonds is gone. So it becomes kind of resistant to oxidation. And we will mention this real quick. But you need to know, lipids hydrogenation is only partially. This is some simple concept. All the organic chemistry reaction is reversible. You know, when you're taking organic chemistry class, you're taking 3 hours, almost a whole day until evening. You've been sitting there. Why it takes so long? Because every reaction wants to reach a status, a stable status, but it never reached it, and always come back for something. Because 99.9%, almost 100% organic reaction is reversible. So the same thing here, hydrogenation is only partial, not will be completed. And there is 2 different types of the hydrogenation will be happen. Is selective, adverse, non-selective. Now what is selective? We want to find the place to add hydrogen at most vulnerable, which we say most unsaturated place. We can say most vulnerable place. And non-selective, you just do it radically. And what happened for the selective? Selective usually will be increased with increasing of the vessel, that closed vessel temperature, and decrease with increasing pressure and agitation. When you see the table here, you can find, let's say peanuts. We have a very non-selective and moderate selective hydrogenation. You see, saturated fatty acids, of course, it's decreased. You will see the oleic acid is actually increased a little bit, but linoleic acids is significantly decreased. So that tells us the higher the selective, the lower the poly unsaturated, and the higher the mono unsaturated. Okay? So oleic acids is the mono unsaturated. That is, and we will mention again. And linoleic acids, okay, that's linoleic. Stearic acids 18, chlorine 0. So you can see cottonseed decreased of the saturated fatty acids. Okay, oleic acids is increased from 48.5 to 56 to 64.5. Linoleic acids almost to 0, from 12 to 4%. So with this selective hydrogenation, this polyunsaturated fatty acids amount is decreased. Mono unsaturated fatty acids, oleic acid is increased. And saturated fatty acids is actually decreased slightly a little bit. Okay, now we already mentioned it's most resistant to oxidation. However, during the hydrogenation, especially partial hydrogenation, it always have trans isomer will be generated. How many trans isomer in margarine? 24% average trans. How many in shortenings? 22 to 46%. Pretty high. Okay, why it will happen? Our textbook described it very simple. And I think it described it very well. Okay. This guy is double bonds. We do hydrogenation. Okay? We add hydrogen. We added it. This is kind of like you give a product to water. Absorption. So we call this absorption of lipids. Or absorption of lipids. Kind of. But you know, hydrogenation is reversible. So it's very easy. This goes out. Which means they go that way. This happened is desorption of lipids. Of course, this is a quotation mark. Not really. We just understand it like that. During this desorption, the products want to find a very stable status to try to stop the reaction. Therefore, compared to the cis configuration, trans is more stable. Therefore, the trans isomer will be generated and even dominant in some of the products. And we learned it before, usually the first position of those double bonds is more vulnerable, more easy to have reverse reaction, which means fatty acids desorption. And then the trans fatty acids and the trans isomer will create because that's a more stable status. Okay, our textbook describes this very well. So hydrogenation. Now, one more thing we find it. During this desorption, what happened? This double bond will be moving, maybe move to here, maybe move to here. That is called a migration, the double bonds migration. Which means they move around and they usually will be moved further from the ester bonds. So this is some research what they did. This is oleic acids from margarine. This is a cis. The right side is trans. What happened? Can you see that? The double bond position, there is 18 carbon, could be at 7 to 16. And the highest happened is in 9. So the double bonds, the different position, the composition is all, the frequency is between 0.9 to 63.6, a very wide range of the frequency. This is for the cis. And for the trans, you also can see the double bond position could be at 6 all the way to 16. And the peak is at the middle, actually. Somewhere 9, 10, 11 position, the double bond is dominant between 37.3 to 21.7. So this is kind of like a very obviously happening. Multiple locations have double bonds. We call it a double bond migration. Happened during the hydrogenation process. Actually, it happened from the reversible. When you have a hydrogenation, it's only partial, then they reverse it. Because they try to find a more stable status. But you can understand it's never reached there. That's why there's so many intermediate products here. So when they combined, they have happened is double bond migration. Okay? So very easy to say, after hydrogenation, in margarine products, it does not matter cis or trans, there is a multiple location showing double bond. That is called double bond migration. Okay, so we finished talking about these two reactions. We're gonna spend time talk about the very important concept in this class, in this section, which is auto-oxidation. Now, before we do that, we still want to revise it, review it, why it is important. So I talked to Tim in the morning. We were talking about which one will be impacted bacteria will survive during the thermal activation. I said the fatty acids is very important. because your feeds water activity is very low. So if you still remember this guy, we have 3 layers. Okay, this is mono. Okay, additional. And this is capillary. Free water. 2 free water. Your feed is right here. Is the polyphenol 0.3, 0.7, is 1.0. Your feed is right here. If you still remember the curve, here, more important is oxidation of lipids. Therefore, for any of the products, water activity is lower. This is going to be a major concern. That's where we're going to talk. Then we move to here, mirrored reaction. Move to here, bacteria sporage. Bacterial sporage. We're all going to cover in this lecture. Okay? So that's why we want to mention the oxidation of lipids first. So we're going to talk about what is called auto-oxidation of lipids. I will give a definition a little bit from what we want to slides. This is lipids or fatty acids in food products, in foods, spontaneously reacted with oxygen, generate of flavor or volatile compounds, and destroy the quality of the fatty acid products, cause rancidity. Now, what is this off flavor comes? This is aldehyde coming from. Okay? So, the definition is fatty acids in food products, which is spontaneously reacted with oxygen, generates the products, primary, secondary, to tertiary, and destroy the flavor. We call it oxidative deterioration, terminology called rancidity. But we mentioned a couple of times, we're going to talk about the details. Of course, this happens is those lipids containing unsaturated double bonds. Okay, what type of the products will be generated? We already mentioned aldehyde. That will be one of the products. Could generate alcohol. Could generate ketones. Ketones not really necessary. Alcohol sometimes. Most of the time is aldehyde. And I gave you a good example what is going to happen. We didn't recognize this too much because most of the foods what we are eating is meat, fresh produce that didn't fit this category. A good example, we don't express it, is a lard becomes sweet. I use lard to cooking sometimes. If you put the lard in the refrigerator too long, about like 6 months or 1 year, when you take it out, you just taste a little bit. Looks like a candy, that's not good. That's a lard that has already been destroyed or like, let's say, rancidity. We have another terminology for that later on. We'll say it's called the flavor reversion, but does not mean the flavor comes back. which means there is a bad flavor, additional undesirable flavor is added. So a good example is lard becomes sweet, or other fatty acids products become suddenly taste sweet. Does not mean it's good. That's not good. Okay. Okay. What are the factors to impact the autooxidation? Number one is the presence of oxygen. This is everybody knows. Okay. Now somebody gonna say, how about if we completely remove oxygen? Then nothing gonna happen. It's impossible, technically. And sometimes we need oxygen. For example, when you have beef, you know all the beef, they don't do vacuum package. You see all the beef, they don't do vacuum package. They use a PVC film, just Arabic package, and put on the display case. And you see sometimes it's a very bright red color, and you like it. Because oxymyoglobin reacted with oxygen become myoglobin. Deoxymyoglobin become myoglobin become oxymyoglobin. We'll mention real quick in the color section. Then showed you those bright red color. So we need that color to attract the consumers or customers to buy it. If all the foods is vacuum packaged, without the oxygen, you won't show a good color. Although you can prevent somehow the rancidity. So it's technically impossible to take out all the oxygen. Although theoretically yes, but it's not. Okay, so the presence of oxygen. Second, sometimes we need to know the presence of some of the peroxide, which means pre-oxidized products, the presence of peroxide. The third, of course, unsaturated. How unsaturated it is? Where is the double bonds? Then location of double bonds. If it's conjugated, like linoleic acids, it's more easy to have oxidation compared to unconjugated, like oleic acids. Number four, exposure to light, metal, and even a heat. Which means some of these external factors. Number five, it's related to temperature. How the storage temperature. Number six, it's related to the packaging. What are the packaging machine? What are the packaging material we are using? That is also going to be impacted. Vacuum package compare Arabic storage will have a different results. Okay. Last one. Sometimes we using chemical antioxidants. That also could be impact the results of the autooxidation.